These are the challenge questions from Book 2 Review Exercise 1. Let's just go into it. So we've got a we've got a circle with center M, which is between A and B. So we should probably go about finding A and B. So A is on the uh, line f of x, and it's got a positive gradient. So that must be the bit where the mod is timesing it by -1 to make that into a positive gradient there. And then this bit over here to find B, the mod must have been doing nothing because you've got a negative gradient on that black line. So okay, to find B, we're just going to set this without the mod function equal to the red line, which is this, and we'll solve that. We'll get x is equals to 2, and then if you sub that in there, you'll get y is 0. And then the opposite for A, right? So for A, again, this is a positive gradient here, so that must be being times by -1 to get that to happen. So we'll do that, and we'll try and solve this. Obviously, we'll get x -6. We'll put that back into either one of these two. It doesn't matter, but you'll eventually get 6 as your y coordinate. So that's good. That means the center is I mean, we can, I guess, work it out. It's going to be what, 2, 3? Not that it really matters, does it? Oh, it will do for the equation of circle, of course. So the center is 2, 3. Sorry, -2, 3, of course. And then we can work out, during Pythagoras, the radius. So it's 4 across and 3 up. So we all recognize the 3, 4, 5 triangle. And the radius is going to be 5. So we're going to have 5 squared over here. Next, it asks us to work out the triangle A to P to B. So they've asked us to work out scaling triangles a lot. What I'm going to do is I'm going to set this bit of the line here equal to the circle. I'm going to essentially solve that equal to the circle because that allows me to find P. Obviously, I need the coordinates of P to work out this triangle here, APB. So, okay, well, like I said, this part of the line is when that's being times by -1, so it's going to be this. And then the circle is this, so substitute all of that in for y, like I have done here. And then obviously simplify all of this before you start squaring it, otherwise you're making life very hard for yourself. Then square everything out, collect everything together, solve a quadratic, and you eventually end up with either 6 or 7. Of course, the answer -6 makes a lot of sense because that's this point here, so therefore this is when x is -7. You can put -7 back into here or back into the circle, it doesn't really matter. Either way, you'll end up with a y coordinate of 3. And now we just need to find the area of this scaling triangle here, which looks like this. I've just realized it's not a scaling triangle. It's right angled because this is the diameter of the circle. And so therefore I could have just done a half times this length times this length. But I didn't notice that I could do that at the time because I'm an idiot. And because they've asked me so many triangle areas before that I think I just did this on autopilot. I just drew a big box around it. I said, okay, well, the area of the box is just 9 times 6. And then I just took away these 3 triangles here, these 3 right angle triangles. So instead of working out the area of 1 right angle triangle, what I chose to do was work out the area of a rectangle and then 3 right angle triangles and then take them away because I'm a moron. But in either case, you're going to end up with the answer of 15, and that'll be that done. Given we've got a recurrence relation for a sequence here, now if a1 is m, that means the first term is m, the second term is m plus k, the third term is m plus k, and so therefore the difference between every term is k. So I can just say the sum up to the first, say, n terms is just following this formula, where the first term is m, and the difference is k. Now the sum from the terms 6 to 11 is going to be the sum of the terms from 1 to 11 minus the sum of the terms from 1 to 5. And likewise from 12 to 15 is sum from 1 to 15 minus 1 to 11. So what I can do is I can just use this formula 4 times in here, with the n as being 11, 5, 15, and 11. Each time with a always being m and k, and difference always being k. I can add this to both sides, this bit here, because notice how these are the same, to just get 2 lots of this, which just means cancelling that 2. Double everything here, I guess, expand everything out, everything cancels except the thing they want you to cancel, and you end up with your answer. Another modulus question then, so this root here is going to be, the red curve is acting normally, so that's, the red is q, so we just take the inside of this. The black curve is upside down, so we minus all of this, and we set those equal to each other, and you end up with this quadratic, which solves to make this. Now I'm going to pretend that I can't work out whether it's 19 plus this or 19 minus this, and you'll see why I'm being lazy in a second. This intersection here, the red curve is upside down, so take the minus of this, and so is the black still, so take the minus of that. This time nicely the x squareds will cancel, you just end up with this, and you get x is 16 over 3. Now at this point I can work out which one of these this is really easily, because 19 plus root 41 is like 19 plus 6, which is 25 over 4, is a bit bigger than 6, whereas this is less than 6, so this needs to be 19 minus root 41. But when you look for this intersection here, I could have also considered the fact that I know where that root is to find whether this was bigger or less than which one of these two it is, but anyway. This is the red one upside down, but the black one the right way up. So this one's the same, and this one's times by -1. But notice how this equation is exactly the same as this one. It's just the other side has been times by -1, which of course doesn't make a difference. So the solution to this is just the same as it was before, which is this. And therefore it must be the minus version, sorry, the plus version, because we already had the minus version. So those would be the three answers to this question here. As soon as you see log of something over something else, do the log law that says that log of that minus log of that. So the left-hand side is this. Now just put all the numbers in. When n is 1, what is going on? Oh, sorry. When you've got 1 here, you just get 3, and then when it's 2, you get 5, and then 7, and so on, all the way up to when you put in 40, you get 81. And then you take away, when you put in 1, you get 1, and then 3, and then 5, and so on. But notice how this is log 3 base 3 minus the same thing, and 5 minus the same thing, because this minus here, and 7 minus the same thing. In fact, everything will cancel except for this log 381, which doesn't have anything to go away with, and this one, which likewise doesn't have anything here. It's called a telescoping series, so it's just going to be this term minus that term. This term is, of course, 0. This term is 4, because it's 3 to the power 4. Bring the 4 out front, and you send the answer of 4, which is the right-hand side. Number 5, then, the graph f of x is transformed interestingly by this transformation. You may never have seen of this transformation before, even though you think you have, because it's kind of a weird transformation. You stretch the graph, or squash the graph factor a horizontally, and then you move it to the left with b, except you don't. You move it to the left by b over a. Once you've done this squash, the movement isn't the same as it would normally be, and I can kind of prove that if you go into here. So here's just a very simple graph, x squared. If you squash it factor a, of course, this does the usual thing. So factor, let's make a the 2. This does the usual thing. It makes it a bit taller. But now notice if I move it, quote unquote, 1 to the right, it actually only moves 0.5 to the right, because it's moving not by 1, but by 1 over 2. Right? Because you can kind of imagine the entire graph has been squashed, not just the curve that you've drawn. And so then any movement of 1 is only a move of a half. And likewise, if you move it 2 to the side, that's when you move it 1 instead. So the movement is only a factor b over a, not a movement of b. And so an xy coordinate has become x over a, because you squashed it factor a, minus, and then you only moved it b over a to the right. And so invariant points, of course, stay in the same place. But notice how through all of this, the y coordinate didn't change because it's all a horizontal thing. So therefore, all we need x to equal this new coordinate x over a minus b over a. We can times everything by a. We can take away xa and add b to both sides, factorize out the x, and then divide, and we'll end up with what they wanted us to get.